so lesson 1, we are going to be focusing on the equation of a line. So as a reminder, what is the equation of a line? Y equals mx plus b. And the m represents the slope, and the b represents the y-intercept. Okay, as long as you remember this, you should be fine. Sorry, one more thing to remember. What is the equation for slope? Yes, y2 minus y1 over x2 minus x1. Okay, so this is recap from stuff we already know, right? So we're going to use this idea to help build onto our next section. The word tangent comes from the Latin word tangens. It means touching and like barely touching. So when we talk about a tangent line, when we look at a graph, we choose a point on that graph. Let's say this point here. And the tangent line is a straight line that comes very, very close to the graph, touches it only at one point and moves on. So this would be the tangent. Okay, on a graph such as a cubic, we run into a little bit of an issue because cubic goes on and on forever in both directions. So if I say that my tangent line is going to be on this spot here, this is my tangent. If I draw my tangent too long, I'm going to run into this spot here. And so instead, we call this a local tangent. Local tangent. Because we are interested in the tangent line for this specific spot on the graph. And yes, we know that it'll eventually touch the point on another graph in this case, but we're just focusing on this section. So in this area, it is the tangent line. Okay, now a secant line is a line on a curve, but that touches it in two different points. So for example, I'll use a green one for this example here. I could say these 2 points, the secant line is the line that cuts through 2 points. Cuts through 2 points. So this is what we refer to as a secant line. It's cutting our graph in at least 2 spots. And of course, as you can imagine, I can pick any 2 spots, so I can make them far apart, or I can make them very, very close together, right? I can bring this closer together, and my secant line now looks like that. One of the key things I also want us to remember, this is, we had talked about it the other day, we are able to use the points on a graph of a line in order to find this equation mx plus b. We know that the equation for slope requires 2 points. We only need 1 point in order to find the equation, but we can use 2 points in order to find the slope because we have this rise over run equation, right? If I put my numerator and denominator into brackets, I could also set up this equation by rearranging it. If I move the x bracket over to the other side, I end up with this equation. And I could say, hey, you know what? Instead of y2 and y and x2, I'm just going to call them a random x and y because I can choose any point. And instead of x1, y1, I'm going to call those x naught, y naught. So a little circle. You can think of it as the original point. I'm going to use that as my base point. And I can rearrange this further to say m x minus x naught plus y naught equals y. And now I have the equation in mx plus b form, but using, rather than the y-intercept, right? If I had a y-intercept, my x naught would be 0 and my y naught would be b. But now I don't need the x-intercept. I can use any point to set up this line equation, which is going to be very useful for us because we're going to deal with graphs that are not lines, right? So we want to find an equation of a tangent somewhere on a curve, and to do this, we need 1 point. So the problem is we have, I'm going to write this out in English language for one time only. We have 1 point. Let's call it P, our original point. But to get the slope, we need 2 points. So in order for us to do that, essentially, we're going to create a secant line. We're going to cut the graph in 2 points so that we are able to find the slope, and therefore we're able to find the y equals mx plus b kind of equation. So we are going to approximate the slope by choosing.
Wait, why does it say to get slope we 2 points?
Need 2 points. Thank you. This is why I'm a mathlete and not an athlete or an English teacher. I'm also ESL. I'm many things, but I'm good at spelling in English is not one of them. Okay, so we're going to approximate the slope by choosing a nearby point, and this time we're going to call the second point Q, and find the slope. And the way that we're going to identify this is by calling it slope M sub PQ. So the slope of the line from P to Q. We're going to use the point of interest as our original point, and we're going to choose a smart second point in order to find the slope at that point, at the point of interest. Okay, so here's how it's going to work. Let us sketch a little graph here. So let's say we have a curve like this. Okay, and I'm interested in the tangent at point P. Now the tangent, remember, is the line that only touches the graph at point P, which means I need a slope. Tangents are all about the slope of our line. In order to find the slope, in order to find my y equals mx plus b, I need a secondary point. So I'm going to choose point Q here. So the pink line represents the slope of the tangent of point P. But I don't know it, I can't find it. So the green line is going to be our secant line. It's going to go through, oops, P and Q. This is why I said it's nice if you guys have rulers. Connect these 2 dots. Miss Gordon is struggling with her non-existent ruler. Oh, here. Can I turn it? Ooh, I didn't know I had a digital ruler. There it is. Okay. Perfect. Go away, ruler. There it is. This is going to be my slope M, P, Q. This is the slope of the secant line between P and Q. And you're going to see that the difference is, let's look at their coordinates. Here's P, and here is Q. I'm going to zoom in here so we can see it a little bit closer. Let's say that the coordinates for P are A and B, I guess. The y coordinates are less important in this point, in this particular example, but that's fine. And we're going to say we're choosing an x value that is a certain distance away. So let's call this distance h. So this coordinate is a plus h away from the original. Okay, so the way that we can find the equation of this tangent, the slope, sorry, remember y2 minus y1 over x2 minus x1. Well, we have a function here. This represents x1 and this represents x2. So if I find the slope, this would be the function at a plus h, the extra distance, minus the function at the original distance. Those are my y values, right? And for my x's, my extra distance is a plus h. My original distance is a. And so if I simplify this further, I'll have f of a plus h, so the extra bit minus the original. And in the bottom, I can actually just expand this, right? A minus a cancels. I'm left with just h in the bottom.
That's good.
Yes.
But for this,
Yes.
like we would have to make it as close as to the actual slope.
Yes.
We wouldn't we have to state the limit that h is as close, going closer to
Yes,
zero?
that's my next move. So the way that we define this is we call this a limit. We want to take this and say that h approaches 0, meaning I want to take this distance and slowly make it smaller and smaller and smaller. Make the difference, the h distance, as close to 0 as humanly possible, because then those 2 points get closer and closer and closer together, and that's going to give me my tangent line. So, sorry, I put the equal sign in the wrong spot. This limit, the limit as h approaches 0, that's how we express this in English language. The limit as h gets closer to 0 is the difference in height over the difference in width. And this is going to give us the slope of the tangent. As P and Q get closer and closer together, as that distance gets smaller and smaller, then we're going to get the slope of the tangent. Okay, there's another way I could write this. I could, instead of saying a plus h, I could just give them 2 different names. I could say, for example, let's call this my original point A, and I'm going to call this new point X. So A is my original point and X is my new point. So I don't have the plus H bit. I could rewrite this. I'm not going to redraw the graph because it's exactly the same idea. The slope of the tangent now is going to be the limit. And this time it's going to say as X gets closer to A. That would be a different way of writing it. And then my height would be the function at X, some new number, minus the original function at A, my original point, over X minus A. So there's 2 different ways to write it. Either you're choosing 2 points and allowing the second point to get closer, or you're choosing a distance that's far away and making the distance go to 0, get closer and closer. The reason we have 2 ways to write it is because depending on the function that we have, the equation that we have, sometimes one way is just easier than the other. But either way is fine. Yeah, the limit is just saying, this is saying we want to get as close to A as possible. This is saying I want to solve this so that H goes to 0 or gets as close to 0 as possible. And when we're saying the limit, what we're doing is we're comparing the slope when Q is far away, and we get it closer and closer and closer and closer. And rather than doing that math 10 times, this symbol just signifies that's what we're doing, is we're we're measuring it as it comes close and gets essentially on the same point as P. Yes.
But if distance is 0, if h is 0, wouldn't that undefine the slope?
Fantastic segue. Let's flip the page. If h is 0, then we have an undefined denominator, which we are not allowed to have. Boo, that's not good. Okay, this is where we're going to use our TI-83s. If I could ask you to pull those out. I'm going to get my digital one here for you. So we are going to look at a quadratic that we are all very familiar with, x squared, and we're interested in the point 1, 1. And we want the tangent at that line. So I'm going to show you how to use our calculator, but for right now, let's just do some by hand math. We know the function will look like this. 0, 0, 1, 1, 2, 4, and so on. So this is what my function looks like. And I'm interested in this point here, 1, 1. In order to take an accurate limit, we need to take a look at what is it going to look like from both sides. So let's do some math here. Let's choose a point Q. Doesn't matter where it is, but let's say it's somewhere here. Let's call this point our Q. And the coordinates for Q are going to be, what are we going to say? X and x squared. Another way to think of this is x and this is f of x. Those are the coordinates. Because I don't want to pick a particular point because I want to bring that point Q close to point P. So I'm just going to use generic x. So in my slope equation from before, right, this is going to be f of x. I hear some chatting. Did I confuse someone? Okay, minus f of a. Remember that a represents our original point. So this is a, f of a. Oops, a, not x, Miss Gordon. There we go, a. Where we have the point, we know the numbers of the original point are 1, 1. Over x minus a. So now I'm going to put in the actual stuff that I have. F of x is x squared minus, what is f of a? My original point. I know the original point, it's 1. Divided by x minus my original point, 1. Okay, so this is the slope. What I want to figure out is, what is it going to look like if I choose, let Q have the coordinates 2, 4. If I chose Q from here, what would my slope be? Yes, ma'am.
Why don't we use the equation to x plus 1?
Yeah, because it's a difference of squares, right? So the x minus 1 just cancels out with x minus 1 on top, which leaves x plus 1.
True, but then you have a non-permissible value that you may miss. If you did that, what you're saying is the distance is 0.
Oh, we can do the non-permissible value first and then simplify and state the non-permissible at the bottom.
Okay. I'll bite. Here we go. X plus 1, x minus 1 over x minus 1.
So we know x cannot.
What's our non-permissible value?
1.
Where is the point of interest?
So
That's our problem. We want to know the slope at the point of interest. If we cancel the point of interest, then what are we doing?
Well, that's exactly the point, right? If the limit reaches 0, we can't have that the point of interest.
But we need a number.
Yeah.
So we can't cancel the point of interest because we need the number at the point of interest. Roll with me. We're getting there. All answers will be revealed to you soon. Okay, so we don't want to do this. It's simplified enough. We are strong enough to do this. Let's take these points and plug them in here. The m of q, if q is at the point 2, 4, is 2 squared minus 1 over 2 minus 1. This gives me 3 over 1. So the slope is 3 if our secant point is at Q with the coordinates 2 and 4. Okay, now I want to approach 1, 1. And we're going to approach 1, 1 from the right, but I don't want to have to do this calculation over and over and over again. So we are going to go to our graphing calculator. We are going to go to the y equals button, top left, clear anything that's in there. And I want you to write the slope equation, this one. Okay, so remember your brackets because we have a denominator with 2 things and a numerator with 2 things. X squared minus 1, close bracket, divided by x minus 1, close bracket. Use the arrows to go back and forth. And I think I just missed a squared there, so let me try that again. Back, back, back. Or here, maybe if I can just clear it. X squared minus 1 over x minus 1. Okay, now I want to be able to do the table of values, right? So I want to calculate all the different possibilities. So I'm going to go to second trace because the word calculate is on top of the trace button. Ooh, that did not work. Let me try again. Second. What am I missing? Oh, right, table of values, Miss Gordon. Second table, the very last one on the top right, my bad.
So how do we go back from calculate to second function? Oh.
You can just type second graph. It'll take you to the table window. Are you here?
Yes.
Okay, so let's say x is 2, enter. Mine is not entering correctly. Let's check my mode. I'm going to click on mode.
Wait, I think you just use the arrows to go up and down.
You can use the arrows to go up and down, yep. Where is my, oh, this is in French. That's why I'm having trouble. Sorry, guys. I've forgotten how to change the thing to ask. I did this with you last week. Sorry. Somebody remind me how I did it. Second format, maybe? No. Table set. Yes. Where is table set? Sorry, mine is in French. I'm trying to find my buttons, but I'm not reading it. Second at the top. There we go. Yay. And I wanted to go down to independent and ask. Thank you. My French is not doing me any favors today. Okay, so second window will get you here and make sure that independent is set to ask. Now I'm going to go to my table. There we go. If I type 2, I should get 3. And that's this right here. I'm saying if x is 2, what is the slope? The slope is 3. Now I want to go where x is greater than 1, because 1 is my point of interest, but less than 3. So I want you to try these numbers. 2, 1.5, 1.1, 1.01, 1.0001, right? Because I don't want to cross the boundary of x equals 1, but I want to be less than 2. So 1.5, 1.1, 1.01, 1.0001. And you can see we're getting closer and closer and closer to the number 2. So this is giving me 3, 2.5, I think 2.1 was the next one, 2.01, 2.0001. So we can see that the numbers are approaching the number 2. So we can almost say that we're pretty sure this tangent at the point of interest, 1, 1 is 2. But before we say that, we need to check the other side. So now I want to look at numbers that are less than 1, but are getting close to 1. So I'm going to go down to 0, 0.5, 0.9, getting closer and closer to 1, but not actually reaching it. Lots of 9s there. So if x is 0, my slope is 1. If x is 0.5, it's 1.5. 0.9, 0.99, 0.999. Enter. Okay, and you can see this goes to 1.999, 1.99, 1.9. So as I get closer and closer and closer to 1, this approaches 2 as well. So as my x values get close to 1, so you see from both sides, left and right, from the small side getting bigger to 1, from the big side getting smaller to 1, this is what this limit is saying. As x approaches the value 1, the slope is approaching the number 2. So the slope at that point is 2. It's really important to understand that this is only the slope at that point. If I changed my original coordinate P, I would have a completely different number. Yes, ma'am.
Why isn't your slope negative if we are coming from the left side of that point?
We're interested in just the value. If we look at our picture, the graph is going in the positive direction, so my tangent line would be a positive slope line. Yep. Any other questions? Okay. So I want you to try, oh, sorry, the equation of the line. We now know the slope. M equals x squared minus 1 over x minus 1. And we know based on the limit that we just did that the answer is 2. I'm going to rearrange this into point slope form. Okay. So in my point slope form, we have, oh, what did I do here? X minus x naught plus y naught. This is from the previous page. So our slope we put in here, and our key point P was 1, 1. So the equation of the line, of the tangent line, is going to be 2 any x minus the original point plus 1. And of course, if you expand and collect like terms, you could write it in just regular mx plus b form. This will give you 2x minus 1. Either of these forms is correct. This way, as long as you have a key point and your slope, you can always set it up. The last way there is just a simplification. Yes, sir.
When you use limits, you get the slope of the entire graph,
No,
but just of 2 points.
just of the single point. At point P, the slope is 2. If I change that point, I would have to redo the calculation up here. Right? If I now chose what is the point where x is 3 and what's 3 squared? 9. Then I would have to change this to a 9 here and a 3 here, and now I would have a completely different equation for slope, and I have to redo the process. Okay, so the slope very much depends on what is my key point. I saw another hand.
Why
Granberry.
can't we just use a tangent line?
Pardon me?
Why can't we just use a tangent line instead of using 2 points?
Because how do you know what the slope of the tangent line is?
By using the graph.
So by using observation. Yeah, but your pencil and your ruler are thick and your eyes are inaccurate. And the definition of a tangent line is a line that touches the graph specifically at one point. So if I'm looking at the point is 1, 1, and the tangent line at 1, 1 is 2, that tangent line at 1.001 is different than the tangent line at 1. So it's got to be very precise. And so that's why we use a mathematical method. Yes, sir.
So basically what we just talked about is that at the value that causes an error in our
In your limit.
equation
Yep.
is that, so that's our limit.
Essentially, yes.
Okay.
When we're using a key point, we are looking for what is the graph, what's the tendencies? What is it approaching? And as long as the numbers from the left and the right, the ones that are slightly smaller and slightly bigger, are aligned, we can see that they are both approaching 2. We can say then the slope at that point is 2. We will get more and more accurate ways of doing this. This is an intro to the theory behind how tangent lines are calculated. Yes.
Does the x necessarily like approaches the non-conventional line?
Yes. Because we want our second point to be on top of the original point, which means the difference between the 2 points is 0. So it's always going to be essentially a non-permissible. Yeah.
And like can limits approach negative numbers?
Yes. Which we will get to
And
those.
where do you put the negative? Do you straight up put it like?
You're jumping ahead. We will, yes, the answer to your question is yes. And where we put the negatives, we will get to when we get to that section. Armand.
Is the second point always above the first point? Like, how do you know which one's the second point?
Your original point is the thing that you are minusing. So it comes second. Good
So if
question.
you use this point that's left towards the point of interest, it's gonna be to give us a negative.
Well, you get a negative numerator and denominator because it's less than,
Yeah.
so which ends up being positive. Yeah. Okay. We have time for one more example, so I'm not going to get to the end of this